Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of electrical fields. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left-hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you're writing full sentences and show your full working out. Whilst in the right-hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. How should you be revising for A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep books and the textbook to learn the key ideas of the course. You may wish to make mind maps or to write out the notes yourself. Second step is to test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Finally, practice exam style questions. Use exam preparation books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. You may wish to download your own examination past papers to do this. So, learn the key facts, test yourself, practice exam style questions. So what are we covering today? We are looking at electrical fields. So what are the key facts to do with electrical fields? Well, we've got Coulomb's law, which is the force between 2 point charges in a vacuum, where F is equal to Q1, Q2 over 4 pi epsilon 0 r squared, where Q1 and Q2 are the charges, r is the distance between the charges, epsilon 0 is the permittivity of free space. Now we can assume air is approximately the same as a vacuum for most practical calculations. Now for a charged sphere, we treat the charge as concentrated at the centre as if it were a point charge. Now we also know that electrostatic forces are vastly stronger than gravitational forces at the subatomic scale. For the electrical field strength, the electrical field lines show the direction of a force on a positive test charge. The electrical field strength is force over charge, or the force per unit charge in newtons per coulomb. The electrical field strength of a uniform field between parallel plates is equal to V over d, where V is the potential difference and d is the separation of the plate. The radial field around a point charge is E is equal to Q over 4 pi epsilon 0 r squared. The work done on a charge is equal to Q times by a potential difference. Now the charged particle trajectories are important, as when they enter a uniform field at right angles, you will get a parabolic path because you got a constant acceleration perpendicular to velocity. Now for electrical potential, absolute electrical potential is the work done per unit charge in bringing a positive test charge from infinity to a point in the field, and it's defined to be 0 at infinity. Our electrical potential difference is the difference in potential between 2 points in a field. The work done on a charge, as we said before, is equal to Q times by the potential difference. There are equipotential surfaces where the potential is constant, and no work is done when moving a charge along an equipotential surface. The radial field potential is equal to Q over 4 pi epsilon 0 r, and our relationship between E and V is E is equal to the change in V over the change in r. So therefore we know that E is going to be equal to the slope of the V against r graph, and the area under the graph is the change in the potential when you've got an E against r graph. So let's now have a look at some general check questions. So, what type of charged object is this? Pause the video now, then unpause the video when you want to go through your answer. We can tell that this is a charged object which is negatively charged, as the field lines are pointing inwards. What type of charged object is this, and how can you tell? This charged object is positively charged, as the field lines are pointing outwards. In electrical field lines, in which directions do electrical field lines point? In electrical field line diagrams, the field lines point in the direction a positive test charge would move in. From a field diagram, how can you determine the electrical field strength of an electrical field? The electrical field strength can be represented by the density of electrical field lines. When do these two objects have the same electrical field? The two objects have the same electrical field in the space up to and to the surface of object 1. When do the two objects have different electrical fields, and why? The two objects have different electrical fields when under the surface of object 1. This is because the charge inside the surface of object 1 will affect its field. What type of electrical field is being produced here? How can you tell? This is a uniform electrical field as the field lines are uniformly spaced apart. What type of electrical field is being produced here? How can you tell? This is a non-uniform electrical field as the field lines are changing in density. Describe what would happen here to a stationary proton. It would accelerate uniformly in the direction of the field lines. Describe what would happen here to the stationary electron. It would accelerate uniformly in the opposite direction to the field lines. Describe what would happen to the stationary proton here. The proton would accelerate in the direction of the field lines, but the acceleration would increase as it moves along as the field line strength increases because the lines are closer together. Describe what would happen here to the stationary electron. The electron would accelerate in opposite directions to the field lines. The acceleration would decrease as it moves along the field, as the field strength decreases as the lines are moving further apart. This diagram shows electrical field lines around three charges, Q1, Q2 and Q3. State the charges of Q1, Q2 and Q3 with a reason. Q1 is a positive charge as the lines are moving away from it. Q2 is a positive as the lines are moving away from it. Q3 is a negative as the lines are moving towards it. In the following diagram, which charge is the more positive charge and which charge is the more negative charge, and why? L is the positively charged object as the field lines are moving away from it. M is a negatively charged object as the field lines are moving towards it. In the following diagram, which charge has the greater magnitude and why? L has the greater magnitude as the field lines are closer together compared to that of M. Describe the force exerted between these two objects. Between the two charged objects, there is a repulsive non-contact electrostatic force. Describe the force exerted between these two objects. Between these two charged objects, there is an attractive non-contact electrostatic force. Which object has the greater electrostatic force acting on it, and why? Both objects have the same magnitude of electrostatic force acting on them as both objects. As in this case, the force is always equal in magnitude on both objects. So, which object has the greater electrostatic force acting on it, and why? Both objects have the same electrostatic force acting on it as the force acting on both bodies is always equal in magnitude. Which object has the greater electrostatic force acting on it, and why? Both objects have the same electrostatic force acting on them as the force acting on both objects is always equal in magnitude. Which object has the greater acceleration, and why? The object with the lower mass will have the greater acceleration as F equals ma. If F is the same for both objects, the lower the mass, the higher the acceleration. If the electrostatic force exerted when the objects are a distance of r apart from the centre of charge to centre of charge is F, what is the electrostatic force exerted on both objects? The force will be linked to F is equal to 1 over 16, as at this point F is proportional to 1 over r squared, so the separation is gone from r to 4r, so the force has therefore been reduced by a factor of 16, r4 squared. In this case, what is the electrostatic force on both objects? It would be F is equal to F over 64. As we know, F is proportional to 1 over r squared. The separation has changed from r to 8r, so the force is now reduced by a factor of 64, 8 squared. In this case, what is the electrostatic force exerted on both objects? Now, so, as a result, as the force would be F over 4, as F is proportional to 1 over r squared. So the separation is doubled from 2r to 4r, so therefore the force is reduced by a factor of 4 because it's 2 squared. If the electrostatic force exerted when the objects are touching, in theory you couldn't use Coulomb's law, but let's just assume we can here, it's F. What is the electrostatic force exerted on both objects? The force would be F over 100, as F is proportional to 1 over r squared. The separation has changed from 2r to 10r, so therefore the force has reduced by a factor of 25, 5 squared. At which point will the charged particle experience the greatest force, and why? The electrical field strength is the same at all 3 points, and the charge of the object is unchanged, so therefore the force applied to the particle is the same at all 3 points. At which point will the charged particle experience the greatest acceleration, and why? As the particle has an unchanging mass and experiences the same force at all 3 points, then the particle experiences the same acceleration at all 3 points. Which laws of physics can be used to explain the motion of the charged particle in this field, and why? The motion of the charged particle can be described by the Suvat equations, as it experiences a constant acceleration in the uniform electrical field. What type of electrical field is produced by the charged object? It's a radial field. What is the relationship between distance and the electrical field strength? Why is this? The electrical field strength is inversely proportional to distance squared, as the electrical field produced is spherical, which has an area proportional to distance squared. From which point does the charged object produce a radial field, and why? The object produces a radial field from the surface of the object, as the charge distribution inside the object can affect the electrical field strength. If the electrical field strength is E at the surface, what is it in T, and why? The electrical field strength at T is E over 9, as the distance from the centre of the object has tripled, so the field strength drops by 3 squared, 9. A conducting sphere is placed inside a second uncharged conducting sphere. What can you deduce regarding the conducting sphere, and why? The conducting sphere is negatively charged, as all of the field lines flow in the direction that a test positive charge would move in. What is the electrical potential at the centre of the charged object, and why? The electrical potential at the centre is 0. This is because at the centre there's an equal amount of negative charge above and below that point. They're producing electrical fields equal in size and opposite in direction, and this gives a potential of 0. What type of electrical potential is around the electron, and why? The potential around the electron is negative. This is because the potential is negative around a negative charge. Electrical fields are denoted in terms of positive charges, and a negative potential indicates attraction. What type of electrical potential is around a proton, and why? The potential around the proton is positive. This is because the potential is positive around a positive charge. The electrical field is denoted in terms of positive charges, and a positive potential indicates repulsion. Which object has the greatest magnitude of electrical potential energy, and why? The electron will have the greatest magnitude of electrical potential energy. The neutron has no charge, so will have no electrical potential energy. Where will both objects have the same electrical potential energy, and why? Both objects will have the same electrical potential energy at infinity, as the electrical potential energy for all objects at infinity is 0. Which object has the greatest magnitude of electrical potential energy, and why? Assume both objects are the same distance from the centre of the sphere. Both objects will have the same magnitude of electrical potential energy, as both objects have the same magnitude of charge and are the same distance from the charged object producing the field. How do, though, the proton and electron in this example have different electrical potentials? Well, the proton has a positive potential as it's positively charged, and the electron has a negative potential as it's negatively charged. So, which object has the greatest magnitude of electrical potential, and why? Proton 1 will, as it's closer to the centre of charge. Why does proton 2 not have half of the potential of proton 1, where r is the radius of the positive charge? Even though v is proportional to 1 over r is measured from the centre of the charged object and not its surface. So what is the difference in potential between proton 1 and proton 2, where r is the radius of the positive charge? Well, proton 1 is 2r from the centre of the sphere. Proton 2 is 4r from the centre of the sphere. So as r has doubled, v will half. What happens to the electrical potential as the proton moves away from the proton producing the electrical field, and why? As it moves away, the potential decreases. This is because it's moving away from the source of repulsion. What happens to the electrical potential eventually as the proton keeps moving away from the proton producing the electrical field as y? Well, eventually the potential will drop to zero as at infinity the potential is equal to zero. Will work be done in this situation, and how do you know? Work will be done in this situation as the proton is moving to areas of different potential in the electrical field. What work is done in this situation? Work is done by the field causing the proton to repel to the other positive charge. What happens to the electrical potential as the proton moves towards the proton producing the electrical field in y? As it moves towards the central proton, the potential increases because it's moving towards the source of repulsion. Is work done in this situation, and how do you know? Work is done in this situation as the proton is moving between areas of different potential in the electrical field. What work is done in this situation? Work must be done to the object, energy is inputted into the system to overcome the electrostatic repulsion. So what happens to the potential as the electron moves away in y? As the electron moves away, the potential increases as the two charges are attracting each other. So what work is done in this situation? Work must be done to the object, energy is inputted into the system to overcome the electrostatic attraction. How can the potential increase in this situation? When there is electrostatic attraction, the potential is negative, so therefore it must increase to equal zero at infinity. So let's have a look at some exam style questions for electrical fields. A research laboratory is developing an ion trap to separate ions of different charges. The trap consists of two small spherical electrodes, each carrying a charge of 2 microcoulombs and separated by a vacuum gap of 12 centimeters. A single ion of charge minus 1.6 times 10 to the minus 19 coulombs is introduced midway between the spheres and is free to move. Calculate the magnitude of the electrostatic force acting on the ion due to one of the charged spheres. Calculate the acceleration of the ion when released from rest. The mass of the ion is 3.2 times 10 to the minus 27 kilograms. Then a student suggests that increasing the electrode separation would improve separation between different ions. Evaluate this claim. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know F is equal to Q1, Q2 over 4 pi epsilon 0 r squared. It's Coulomb's law. So pop in all the values, and remember now that there's going to be a separation of 0.06 meters. So therefore, because it's been introduced midway, so therefore it's 8 times 10 to the minus 13 newtons. Sorry about that. We know for the next question, E is equal to Q over 4 pi epsilon 0 r squared. Pop in all the values. Now remember it's r squared, so it's going to be 0.06 squared. So it's 5 times 10 to the 6 volts per meter. The direction will be from the positive sphere, so the ion will accelerate towards one of the spheres. We then use F is equal to EQ, so therefore F is going to be equal to 8 times 10 to the minus 13 newtons. A is equal to F over M, so we pop in all the values and we get 2.5 times 10 to the 14 meters per second squared. Now, increasing the separation will decrease the field strength as E is proportional to 1 over r squared. The lower the field will give the smaller the force and the smaller the acceleration. So this makes the ion separation less effective, not more. So the student's claim is incorrect. A greater separation would in fact reduce performance. A prototype medical device is designed to deliver charged particles into biological cells with very high precision. Two small parallel plates 2.5 centimeters apart in a vacuum are charged to create a uniform electrical field. A singly charged ion with a mass of 4.7 times 10 to the minus 26 kilograms and a charge of 1.6 times 10 to the minus 19 coulombs is released from rest at the positive plate and accelerates towards the negative plate. The potential difference between the plates is 320 volts. Determine the force acting on the ion and the work done in moving it across the field. Determine the final speed of the ion when it reaches the positive plate. Then a researcher proposes doubling the plate separation to allow for longer acceleration distance whilst keeping the potential difference constant. Evaluate whether this would affect the final speed of the ion and justify your conclusion. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know E is equal to V over D as it's a uniform electrical field. So we pop in the values and we get 1.28 times 10 to the 4 volts per meter. F is equal to EQ, so you pop that in to be 2.05 times 10 to the minus 15 newtons. Then work done is charge times by potential difference, so it's 5.12 times 10 to the minus 17 joules. We know that in this case the work done is equal to the kinetic energy gained, so it's a half mv squared is equal to 5.12 times 10 to the minus 17 joules. We can rearrange that to get v, so v is the square root of 2e over m. Pop in all the values, you get 1.47 times 10 to the 4 meters per second. Now, doubling d whilst keeping v constant, we know indicates to us that the electrical field strength, which is V over D, will decrease. So the smaller E will lead to a smaller force on the ion, but the work done, which is equal to QV, will stay constant, as neither of those values are changing. So therefore, the final kinetic energy is actually unchanged. So this means that the final speed of the charged ion is actually unaffected. The next question says, two small conducting spheres A and B are placed in a vacuum. Sphere A carries a charge of 4 microcoulombs and sphere B carries a charge of 8 microcoulombs. Both spheres have identical radii and are isolated from other objects. The graph shows how the magnitude electrical field strength E varies with the distance from the centre of each sphere. Without performing a calculation, explain why the electrical field strength around sphere B is greater than that around sphere A. At a certain point P, the electrical field strength due to sphere A is 9 times 10 to the 4 volts per meter. Point Q is twice as far away from sphere A as point P. Explain with reasoning the electrical field strength at point Q. Then two identical negative charges are placed in the region between spheres A and B. One is placed at a point closer to A and the other closer to B. Discuss the differences in the forces experienced, the potential energy, and the acceleration of each charge. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know that both fields will follow E is proportional to Q over R squared. Now since QB is greater than QA, the field strength for B is always going to be greater at the same radius. Next, we know the field again follows the inverse square law. E is proportional to 1 over R squared. So doubling the field strength indicates doubling the distance indicates the field strength becomes 1/4. So at that point, we can work it through to say that it's going to equal 2.25 times 10 to the 4 volts per meter. Now, next one, we know the electrical field strength is greater closer to the more charged sphere. So the force on each charge is equal to EQ, so it's greater for the charge near B. Now, the potential energy is therefore more negative nearer the higher potential, so closer to B. The greater field near B implies a larger electrical force, so a more rapid acceleration. Now, since both charges are equal and negative, they'll experience a force towards the positive spheres. Acceleration is F over m and is higher near B due to the larger force. So we can say that the charge near A moves more slowly with less kinetic energy gained. The next question says, in the late 1700s, Charles Augustin de Coulomb used a torsion balance to investigate the force between two small charged spheres in air. One sphere was fixed in place, the other was suspended on a light rod and rotated when the spheres repelled. The angular displacement of the rod was used as a measure of force. The experiment was repeated for several different separations between the spheres. Coulomb concluded that the force between the charges is inversely proportional to the square of the distances between them. The following data show the measured force of F and separation R. Use the data in the table to show that the electrostatic force is inversely proportional to the square of the separation between the charges. Support your answer with appropriate reasoning and calculations. Describe how Coulomb may have ensured that only the electrostatic force was measured in this experiment. Identify at least two sources of error that would have been difficult to control in the 18th century. And then modern data loggers and sensors allow this experiment to be repeated more precisely. A student finds that plotting log f against log r gives a straight line with a gradient of approximately -2. Explain what this reveals. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how can you prove it? Well, you carry out that k, the constant, is equal to fr squared for each value. Now, when you calculate for each line or row on the table, you can say that k is the same value for each data point, so the data supports the relationship f is proportional to 1 over r squared. Now, using an insulating stand in dry conditions will help to avoid charge leakage. ensure that there's no objects nearby to disturb the electrical field. It is quite difficult to measure very small angular deflections accurately, and air currents or humidity could also interfere with measurements. Now we know F is proportional to r to the power minus n, so taking logs gives us this idea that log F is equal to log K minus n log r. So a straight line with a gradient of minus n implies a power law relationship. As the gradient is equal to minus 2, it tells us that F is proportional to 1 over r squared. So this is strong evidence supporting Coulomb's original result and validates the inverse square law. A lightweight drone designed for atmospheric monitoring accidentally accumulates a small positive charge as it flies near a positively charged spherical communication tower. The tower behaves as a point charge and has a net charge of plus 2 times 10 to the minus 5 coulombs. The drone has a charge of plus 8 times 10 to the minus 9 coulombs and a mass of 2.5 kilograms. At one point, the drone is stationary at a distance of 12 meters from the center of the tower. The drone is then remotely moved to a position further away at 24 meters. Show that the electrical potential at a distance of 12 meters from the center of the tower is approximately 1.5 times 10 to the 4 volts. Calculate the work done by the electrical field as the drone is moved from 12 meters to 24 meters. State whether this is work done on or work done by the field and justify your answer. Then a safety engineer claims that the electrical field strength and potential are both halved when the drone doubles its distance from the tower. Assess the accuracy of this statement. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that V is equal to Q over 4 pi epsilon squared R. So you pop in all the values and you get your answer to be 1.5 times 10 to the 4 volts. Now we can work out the potential difference now at 24. So when you work it through, you can get your answer out and you'll find it to be 7.5 times 10 to the 3 volts. So the potential difference is the two values minus each other. So we get minus 7.5 times 10 to the 3 volts. Now therefore the work done is the charge times by this potential difference, which is minus 6 times 10 to the minus 5 joules. Now the negative sign produced in the answer means that the field does negative work. The drone is moving against repulsion. So the work is done by the external agent, not by the field itself. Finally, electrical potential varies as V is proportional to 1 over R. So when R doubles, V halves, which is correct for the potential. But the electrical field varies as E is proportional to 1 over R squared. So when R doubles, E becomes 1/4. So the engineer was partially correct. The potential halves, but the electrical field strength will reduce more sharply. Two small autonomous satellites A and B are used to study long-range electrostatic repulsion in space. Each satellite has a mass of 120 kilograms and is equipped with small ion engines and an external surface that can be charged. In a test, they are both given identical positive charges of plus 5 millicoulombs. They are released from rest in deep space at a distance of 8 meters apart. Determine the initial acceleration of satellite A. Using the principles of energy conservation, calculate the maximum separation the satellites will reach before coming to rest, assuming no other forces act on them. A graph is plotted showing the electrical field strength at various distances from satellite A and how it varies with distance. The graph follows an inverse square relationship. Explain how the gradient of the VR graph for satellite A is related to this electrical field data, and use your understanding to describe how a plot of potential energy versus distance for satellite A and satellite B would appear. Then a student suggests it would be possible to place a small negatively charged probe at a specific point between the two satellites so that it remains stationary. Would this happen, and why? So pause the video now, then unpause the video when you want to go through your answer. In the first one, F is equal to Q squared over 4 pi epsilon 0 R squared. We say Q squared as they both have the same charge. So we work it through to be 3.5 newtons. A is equal to F over M, so it's 2.9 times 10 to the minus 2 meters per second squared. Now the total energy at the start will be all potential energy. So E is equal to Q squared over 4 pi epsilon 0 R. So we work it all through and we get eventually E to equal 28.1 joules. Now at the max separation, the relative speed will be equal to 0. So therefore all energy is stored at the potential. So we know R is going to be equal to Q over 4 pi epsilon 0 E. Pop in all the values, we get 8 times 10 to the minus 3 meters. So this tells us that the satellites reach 8 kilometers apart before turning. Now the next one, we know the field strength is equal to minus V over E. So at that E over R, my apologies. So the gradient of the VR graph gives you negative E. So the V versus R graph will be negative, a negative curve flattening out with increasing R, like 1 over R. The potential energy graph for A and B will rise steeply at small r's and then flatten, which is consistent with repulsive interactions. Finally, the electrical field due to A and B at a midpoint both point away from each satellite. So for a negative probe, forces act towards the satellite from both directions. So there'll be no stable point unless asymmetry is introduced. So the student's claim is incorrect. There's no point of zero net force between two light charges for the negative probe. So only the possible would be if one was positive and one was negative. The diagram here shows a simplified version of the apparatus used in an experiment to determine the charge on an electron. Negatively charged oil drops are sprayed into a region above two parallel metal plates. The plates are separated by a distance d. The oil drops are allowed to enter the region between the two plates. A potential difference V is applied, which causes an electrical field to be set up between the plates. The diagram shows one oil drop falling between the plates. Add lines to the diagram to show the electrical fields between the plates. V is gradually increased. At a particular value of V, the oil drop stops falling and remains stationary between the plates. Explain this observation. Then the oil drop has a mass m and a charge q and stops falling when V equals 5000 V. Show that Q over m for this oil drop is about 50 microcoulombs per kilogram. D is equal to 2.5 centimeters. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you would draw vertical and equally spaced parallel lines when it should be, because it indicates to us we've got a uniform electrical field, and the arrows point downwards because it is the direction that the positive test charge would move in. Now this tells us there will be an upward electrical force which is equal to the downwards force of weight, so therefore there's no overall resultant force. We know F is equal to EQ, which we know is VQ over D, and that will equal the weight, which is mg. So Q over m is equal to GD over V. Pop in all the values and we get 4.9 times 10 to the minus 5 coulombs per kilogram. Coulomb's law for a force F between point charges Q1 and Q2, which are a distance r apart, is given by the equation F is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Express epsilon 0 in the terms of base units. Electrical fields are caused by both point charges and by parallel plates with a potential difference across them. Describe the differences between the electrical field caused by a point charge and the electrical field between parallel plates. Your answer should include a diagram of each type of field and a reference to electrical field strength. Two small spheres, L and M, are attached to a non-conducting thread and suspended from a point P. Each sphere is given an equal positive charge of 4 times 10 to the minus 7 coulombs. The spheres hang in equilibrium as shown. The mass of each sphere is 2.7 grams. By considering the forces acting on one of the spheres, calculate the tension in the thread and the angle theta. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that F is equal to kg m seconds to the minus 2 because F equals ma. We know that Q, which is charge, is equal to current times by time, so it's going to be amp seconds. So therefore, we pop that into the equation and we cancel them through. Obviously, R will just be m. You get a squared kg to the minus 1, m to the minus 3, seconds to the minus 4. Now, you should have for the parallel plates a minimum of 3 parallel equispaced lines touching the plates. The diagram for the point charge should be 4 equispaced radial lines touching the charged point. Then the diagram of the fields will be correct and pointing in the direction of positive charge will move in. The parallel plate will have an electrical field strength the same at all points, whilst for a point charge, the field strength obeys the inverse square law. Now for this last question, we know the weight of the sphere is mg, so we work it through to be 0.026 newtons. The electrical force is Q1 Q2 over 4 pi epsilon 0 r squared. So you pop that in, work it through to be 0.023 newtons. Vertically, because it's at an angle, we know we can resolve and we get T cos theta equals mg. And horizontally, we resolve, we get T sine theta equals the electrical force. So therefore tan theta, which is sine over cos, is going to be equal to the electrical force over the weight. So it's 0.023 over 0.026 newtons. So we can work out our angle to be 41 degrees. We then can say, well, if we know T, if we know the angle, well, T is mg over cos theta, because we know all the values there. We can then work it through and we get T therefore to equal 0.034 newtons. So, thank you for watching this revision session today on electrical fields. If we've been successful and we've learnt in today's lesson, we can answer A-level physics exam style questions on electrical fields, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. Thank you so much for watching this revision session on AQA A-level physics paper 2 on the topic of electrical fields. Thank you so much and have a lovely day.